the live stream. All good? Great. So thanks everyone for coming out for the morning session today. And yes, so great. So for today's first talk, we have Dean Foster. Dean probably needs no introduction in this workshop, but his work has been highly influential in the field of calibration and prediction over many years. And so we're really excited to have him here and to hear what he has to say today.
Okay, I've been giving versions of this talk for going on 30 years. So so I think my first time I get to play the role of a grand old man. I'm at least two of the three. I'm going to probably go a little bit faster than I normally do because you all do have some ideas. The first time I talk to an audience that could know what calibration was ahead of time. So what I usually do is I just talk to statistics audiences, and for them, this is kind of what I think of as calibration. You have a regression. If your data is on the regression line, you're happy. If your data is not on the regression line, this is bad. And then I spend the rest of the talk talking about how to get your data onto the regression line and standard errors, things like that. And calibration in that sense is anything which is a post-processor, some way to fix up statements you're making about the world after you've seen it. So and it's that definition sort of allows you to extend it to new areas pretty easily. But the other hat they oftentimes wear is game theory. So in game theory, what we care about mostly is incentives. If I ask people just a general knowledge question, will your favorite football team win next weekend? People answer with their enthusiastic belief rather than with actual probabilities. So if you just ask people numbers, they just guess and probably don't mean anything. But if you give them some incentives, for example, if you're playing the game of bridge, and if you on a bridge, there are certain things that actually say are exactly a 50% chance. There are other things that you can do which may be sort of more subjective. If you have probabilities which are not calibrated, you will make bad decisions. So with the right incentives, in game theory, you will end up with good answers. So both of those sort of approaches are ones where I've given talks, drastically. Now, I wanted to get this on the table because this is still going to be my worldview. And so there will be several complexity embarrassments as I go along, where if you want to raise your hand and say, isn't that an exponentially slow algorithm? The answer will probably be yes. Hopefully most of these we can be patched, but there are some points where my co-authors don't, shall we say, entirely care about, computation. Okay, so in particular, I'm going to be focusing on the online problem. That means you're looking at a sequence of forecasts you're trying to make, and your goal is to be calibrated. Now, it's an arbitrary sequence, hence the game theory model. So in game theory, you're trying to say, predict what the other person is going to do. And if you can make good predictions of what they're going to do, you can use those to make decisions yourself about what they're going to do, and kind of everything works out pretty easily. So you can reduce a complex multiplayer game into a single player calibration problem. And that's why game theory works out so nicely. And so that's just to drive the point of what calibration is and isn't. So a sequence of zeros and ones. Your computer people, you can probably figure out this pattern really fast. Odd even. And calibrated is 0.5. Now, not a particularly good forecast, but the key thing about calibration is oftentimes good enough for what you want, particularly in game theory, where you just need to know approximately what the other person is going to do. Now, the point is that there are things that are stupider than 0.5, like say 0.6. That really is a bad estimate of this frequency. Now, we're going to get to a lot today is talking about things which are, better, maybe, So this sequence of say 0.1, 0.9, 0.1, 0.9, when it has said 0.1, it didn't see 10% of the time. So it is not calibrated. When it says 0.9, it sees 100%. So again, it is not calibrated. This forecast then fails the calibration And it's about as far off calibrated as the 0.6 is, by about 0.1 in some sense. But on the other hand, it's hard to think of a situation where you wouldn't really prefer this forecast. It just is more accurate, it's closer. So that's what we're going to try to get, is try to bridge the gap between those two things. Okay, so let's see what. Okay. So calibrated forecast exists. I have to throw out a shout out to my colleague Sudra Hart for the shortest proof. Apply minimax. Now he actually solved that real time in the audience when he first heard me give the talk. I had a really convoluted, long-winded proof, and he realized you could apply minimax theorem and get it instantly. Now, this will be a first chance where you get to be a little bit embarrassed for me. This is a game, nature versus statistician. And you can write it down as a bunch of strategies for nature, a bunch of strategies for statistician. And it's just a matrix which you have to solve the value for. And it just happens to be a 2 to the 2 to the t size matrix cross 2 to the 2 to the t. It's actually bigger than that. It's 1 over epsilon in there, but that gets harder to write down. So this is, not, shall we say, the cleanest way to come up with an algorithm, but it's effective. It says, just solve this huge matrix problem, and that tells you what you're supposed to do. Okay, so he likes this because it does answer it instantly as existence. Okay, so all that game theory, statistics isn't really what I'm going to talk about. I'm going to talk about 2 or 3 ideas that I've been thinking about more recently, and one of them I'm going to call Macau. One of them is called Calibrating, and then lastly I'll be talking a little about maybe some fairness ideas. So those are hopefully closer to multi-calibration. And so effectively, I'm going to do 3 short talks. The third one, I think, is about maybe 3 minutes long. Okay, so the first one is Macau. Now, if your geography is as bad as mine, you probably hadn't heard of this till I don't know how I came across it. Macau is a city in China, which trumps Las Vegas for the amount of gambling that happens by an astronomical amount, maybe 5 to 1 or something like that. So if you think gambling, you should think Macau. And I figured that was a good name. I'm going to be doing a betting sort of approach to things. It's kind of going to be a sequence version of multi-calibration. I'll let you decide whether it's identical, equal to, or just approximately or similar. Then I'll do a paper with Sergio Hart on calibrating. You can always tell Sergio because he likes cute things. And if you've seen one of his talks, they're just full of cute things throughout. So that's his title. And that's a slightly different version of the same thing. And then lastly, I'll say a few words on some fairness ideas and what it is I think we should be calibrating. So what are the things that we should actually be talking about when we think about we'd like to have something to be calibrated? So what should that look like? Okay. So let's start off with Macau. So I'm going to give a quick summary of what it is, because this is something you haven't heard of because I haven't even actually published it yet. Most of the math has been published and written in various other papers, but the sort of naming and sort of combining together is new. Okay, so the idea is we want to do forecasting for decision making. I mean, that kind of is my day job now. I work at Amazon. I was hired to start a forecasting team in New York, and we forecast how many sales we will make of 20 million products. Now, we don't really care about the forecast. What we care about is how many we're going to sell and making sure we have inventory managed ahead of time to have it in stock. So when you order it, we've got it. So it's really, the forecast is a tool to get to a decision. And that's why I sort of thought about this for the past few years and been thinking about how to make sure your forecasts are useful for decision making. Now, it is online. We're invariably forecasting the future we haven't seen. So, as I say, in particular, the future is kind of perniciously evil against us, a little bit at least. This is, every year, people order their gifts for Christmas and they say, well, last year I ordered it 5 days beforehand and most of it arrived on time. I can put it off to 4 days beforehand and the entire distribution shifts. to be a different distribution, slightly, definitely more evil as far as we're concerned. So paranoia is okay, but the key point is, can we make forecasts which will be good for decision making? How do we make that gap? Okay, and the point is that accuracy doesn't always work. The naive story is like, well, yeah, more accuracy should lead to better decision making. And that's kind of generally true. And certainly it's true if you're talking about being closer to probability distribution. But if you're talking about individual sequence, there is no real probability to be close to. There is no real gold standard right answer. So it's kind of nebulous as to how you think about accuracy, except for the point of, I made a prediction, did it correspond to the y variable that I did actually, the outcome that I see? Okay, so the accuracy definition that we will be using is some version of low regret, some version of saying that other forecasts that we could have done shouldn't have done much better than we did. So we want our forecast to be sort of the best of breed. Okay, now this is sort of 2020 hindsight. There's a whole mass of papers doing this. It's been hot topic for, well, going on about 30 years. Okay, so what I'm going to argue is that Macau, or falsifiability, is the right way to think about converting a forecast into a useful forecast. So not just one that is close, but a forecast which you can trust for making decisions. So that's our overall goal. And then the key idea is I'm going to introduce something I call the crazy calibration variable. And if that plus low regret, if you have those two ideas, then you'll have low Macau, which means it's something you can bet on. And if you can bet on things, well, that kind of leads to good decisions, because if you're making bad decisions, you'll be losing a bet against that decision. So you set up your bets to describe how you could go wrong in your decision making, then not losing bets corresponds to making good decisions. Okay, so let me walk through these ideas. Okay, so the idea of falsifiability then is I'm going to take as a bet. I'm going to operationalize it as a way of saying, can someone place a bet against your forecast? So I want to sort of claim that, y hat is a forecast, it kind of should be the expectation or conditional expectation or what have you. But I have no probabilistic model, so I really can't really say that. But what I can do is I can kind of do something that kind of looks very familiar from yesterday. I can have a bet. And I can say a bet will now be a random variable. And it'll tell me when I want to bet either +1 or -1, or depending on personal taste, 0 or 1. Same sort of thing. And my claim is that y hat's supposed to be unbiased estimate for y. So that means that I'm claiming that this is a fair bet. If I thought that this was always positive, well, I should adjust my y hat to make it bigger, I think, and always negative, make it the other way. So then operationalize this. We have our y hat that we're really focusing on. We have, again, this game theoretic approach. B, which is going to be created by an adversary. And so that means we want to look at the worst possible B. So we'll look at a bunch of Bs in some set. And that worst B would be what some other player in a game chooses to annoy us. And then what's a good y hat? Well, the thing which minimizes this sort of Macau. It's kind of sort of like a regret, and it's very close to a multi-calibration. But this expectation is really being mathematically dubiously being used here, because I don't really have probabilities. Okay, and so then what I want to do is I want to find the best thing I could possibly do based on minimizing the worst possible bet. Yes?
Is B a function of the input data?
B can kind of be a function of whatever you want. And so what I'll be doing is I will be putting, say, B in a linear space. And then B will be, say, any linear combination of things in that space. So B might be historical things that you could understand, or in the multi-calibration, B might be subgroups. So B could be properties of the next forecast I'm going to make. As long as I can know what B is before I make the forecast, then I'm home free. So, okay. Okay.
And your expectation is dubious just because you're thinking about this.
Yes. Yeah.
Great.
Yeah.
So,
Okay.
so what's the expectation at the bottom that you are including?
This expectation here,
Yeah.
still dubious. I would do a definition now with actual sequences. So if you replace this by a sum and a limit, then that would probably work out fine. So you know, if expectation is very hard, then this long-term figure object.
Will that be like, should I think of Marty in a few minutes? Why is it fair here? It just seems like
It's if this were an expectation, then y minus its expectation is on average zero.
just zero.
That's all.
Okay.
That's all. Yeah. And we will be sort of doing martingale kind of things a little bit. Yeah.
Just to make sure I understand the order of play, so you make a prediction, and then after having seen someone's prediction, the other player makes the bet. It doesn't matter, I guess.
It kind of does. That if the other person knows how to place bets that you don't know, you'll lose. So if the other person has more information, and if they say they're only going to bet on things which are likely to rain, and you don't know this property that they know about the world, well, then they'll be placing winning bets. So we do want to have B be something that obviously I'm not going to be told you know, what the outcome is going to be of Y, but I need to know whether they're going to be betting on this particular point. Now, it's because it's a max, I really don't know which bet they are placing. So let me actually get to the actually more mathematically precise definition and then see if these answers, you know, questions go away. Okay. So let me start out with my first individual sequence result. And that was an online least squares problem. So the idea is you have a bunch of historic data, you have some X's, you have a Y you're trying to predict. We want to do a linear regression of Y on X. So this is easy to do. We just minimize over a bunch of betas. You know, what's the best linear forecast of the Ys? Now, you know, from Amazon's perspective, all this is ancient news. I don't care about any of it. The only thing I care about is the next possible row. So I care about t plus 1. So that's what I want to think about predicting. And I need these X's. So these X's will then be our bets or things that go into our bets. So I want these X's. I have my beta hat from the previous data where I did know the Y. I can inner product those and get a forecast for Y hat. So this is sort of the real problem that I have to solve in life, where I have my historical data, I predict it once ahead, step ahead, and then, you know, we deal with the future next year out. Now, if doing mathematically, we want to think of this as a sequence. So we will build up all the possible betas going along, and every single beta corresponds to the data that comes above it, and it can be used for predicting that row. So if I multiply it by the X's in that row, that will give me a forecast. So this is online regression, and you know, the F is for me, obviously, but if you don't know how to spell my name, and in fact, some people have cited this Forster under my spelling of the name, he did it a few years later. Basically, it works out nicely. There are several versions of doing least squares. And what it says is that the actual error that I will make, that's how far away my forecast is from the outcome, compared to the best linear combination that I could have, is small. Okay, so no problem. This is a statement about numbers. There's nothing here really about forecasting. You know, there's just a statement about how numbers relate to each other. So the X's kind of could be anything. The X's could say, for example, be previous Y hats. And what's kind of neat about that with Bob Stein, we showed how you can make a forecast better by looking at your previous Y hats without ever looking at a Y. And that goes to what you referred to. We want to preserve martingale properties. We want to have forecasts which have martingale-like properties to them. And so we could identify a martingale by looking at previous forecasts of things and you know, improve a forecast. Now, that sort of makes sense. We're looking at previous y hats. But that's not what I want to do. What I want to do is I want to look at a current y hat. Now, I don't know what y hat is until I make the forecast. But hey, this is math. So if this column of x's was y hat, the theorem still holds. It's just a statement about numbers. Now, I also have the same y hat 4 written over here, and they better mean the same symbol. So that means I won't know what this y hat is until I've done this algebra over here. And if you do algebra in your head, you can see actually it's just simply a linear equation. So life is not too bad. So computationally, we can solve this one. And this is what I call the crazy calibration variable, because we are using a y hat in as a regression variable itself. Okay. And so, yeah.
So why? But you do have y hat of t in the teeth column.
Yes. So I just threw it in here.
Oh.
So I mean, I could throw it anywhere. I just haven't thrown it.
But you're multiplying by beta t minus 1.
Yes. Yeah. That's it. Yeah. It's sort of yeah. So this beta comes from all the data above. And this y hat, I don't know until I have actually seen all the rest of the x's, the beta that comes from above, and then I can solve for y hat. Okay, cool. So Sean Cockney and I did this idea, and it sort of gets some nice calibration. That's how we introduce weak calibration. What we can show then is that if you have this property here, the y minus y hat, when you inner product with the x's, on average is about 0. So it has about square root of t, Macau. So this is now a Macau statement. So now we can sort of make everything fully precise. I have forecasts, they're sequential. I have the outcome, and I have some x's that these are the bets. So I could actually look at 2 times one of the x's, minus a half times the other one. It wouldn't matter. So I could have a linear combination of these x's. Those are my space of possible bets. And no matter what space of possible bets it is, it's going to be about psi squared of t.
Could you define Macau one more time?
So this is actually is our definition. So it's satisfying this thing. So and probably if I want to give it truly as a definition, I just go little o of t, and so the square root of t is kind of more than I would need for a definition. So anything that's small.
Could you go back one slide just really quick and yeah, so this holds when one of the.
So one of the x's were y hat. For some reason, I chose a third one. Yeah. It's still a true theorem about our forecast accuracy will still hold. So it doesn't matter the fact that we don't really know what our forecast is till after we have plugged in the blanks. This is a fixed point, and this is it's happen to be an easy fixed point, because this is the function of the x's, and we don't know what that function is till we actually plug the y hat. Okay, so what we've done here then is Macau is effectively a your normal equation. So statistics, we try to avoid ever computing this minimization. That's sort of nasty. What we'll do instead is we'll solve what's called the normal equations. Normal in the sense that these are orthogonal to each other. And what we know is that the minimizer of this is at exactly the point where this is perfectly orthogonal. So this is a better thing to solve numerically. You have your least squares if and only if you have normal equation. In probability theory, we can talk about a conditional expectation, and that is some function of the x's that minimizes this. Now, actually, in probability, we usually, for some reason, do it the other way around. And if you do the highbrow version of conditional expectation, you say for any other function of this, that product should be 0. That's a normal equation. So in probability, the normal equation holds if and only if the least squares holds. Now, when you do online, we don't really have as good a least squares, so we have, say, low regret. And now we don't really have a normal equation, so we'll have low Macau. It turns out that, so I guess here's again definition. So Macau, I guess I'm allowing different weights on these x's. So on the Macau, so how do these things work out? So the way they work out is because we're talking about sort of a linear space, and that linear space already has y hat in it. Now, when you're doing time series, at any given instant in time, your y hat is a linear combination of the x's, but that linear combination changes. So that means your y hat is not in your linear space. So you don't actually get this automatically. And so in the online world, low regret in this least square sense doesn't mean you have low Macau, and vice versa. Low Macau, if you've satisfied your normal equations, doesn't mean you have low regret in least squares. So you need this extra crazy calibration variable in order to get these two things to be if and only if. Now, the way you prove that is by looking at an actual example. I'm not going to try to walk through that because it's just tedious. Yeah.
So I feel a bit tricked. I mean, here you tell us you have no Macau for alpha is equals 1, but here the definition here.
So here's a proper definition of Macau. Okay.
But can you guarantee that is low, or just for when all the
so we know that so the somewhere I have the theorem. Where's the theorem? Didn't I have a theorem? I guess the previous slide I had the theorem back here. So here this theorem is phrased for a particular x, so a delta function in weights. And if you had a different weighting on these, as long as your weights are constant over time.
Are the coordinates or in the time?
So in the coordinates.
Ah, okay.
So you'd be saying like 2 times this column plus 3 times that column, and you're home free. Okay. Okay. So.
Can you go back to the definition with that one?
This one.
Yeah. So, stupid question, but why is this not maximized when alpha is just either -1 or 1?
You could. It doesn't really matter too much. I mean, the proofs basically just do plus or minus 1 for each x. And it's just, this makes it a space, so it sounds bigger. So it's a linear combination of them. And sometimes I have no idea what actually, I'd say, okay.
So the second, why do you have g of shouldn't, it does depend on x and the other ones, right? I mean, why?
So
why is this not,
we're trying to make f the initial expectation.
okay.
So say f is the initial expectation. If I pick any g, and I can now pick the worst g, which sort of falsifies that as an expectation.
Okay, just because.
So normally it's just phrased for all g of x. It should be exactly 0.
So the issue here is just that you're going from a linear predictors to general predictors.
Yeah.
Like linear space function.
Okay, so can you convert Macau into something useful? Yeah, my sort of internal push is to use this for making decisions. I don't really have a clean answer, but the idea is that suppose I want to solve a problem of online convex optimization. I see a convex function each point in time. It's changing. I want to pick some point that will minimize all these things after the fact. So what I want is I want to say that my ASA, now I'm thinking of that as an action. My action should be, close to having chosen the best action, but I won't know what the best action is till the end of the day. So that's what I'd like to have. So here's our definition again of the regret. So I can now, if I could draw pictures in LaTeX better, I'd draw a picture with a nice little tangent line here. And this would be an obvious statement about tangents of convex functions. And now I can add and subtract a forecast of this gradient. And how am I going to choose the action? Well, I'm going to choose the action at the point where I think the forecast of the gradient is 0. So if I forecast from the gradient, if I forecast it at every point, well, I'm going to choose an action which makes that forecasted value 0. So this term will be 0. And this is a forecast, which I'm multiplying by some weights. Now, I guess it's sort of, I will need the money linear combination for this. Multiplying by A star, well, A star is a constant. So that would be just a weight. I don't know what the weight is ahead of time. And if I also then had A hat as a regression variable, then both of these would be in the span of my space. And so this is a Macau, and it can keep that small by Macau, and this is small by choosing a point which is 0. So that's the idea. Now, where this works the best is in what Sasha and Dylan Foster have done, where they do square CB. They'll do a forecast of a loss, and then they'll just optimize that. Okay. So let's see. Okay. So the proof is pretty straightforward. I'm not going to, pretend that it's obvious as this slide suggested is, but you just draw a quadratic and it kind of works out. Every time I've tried to go through this slide in detail, I've always messed it up. So you have to read the paper. Okay. But the key point is that, typically when I play around with these things in actual fact, you end up with regrets that are log t, because these are continuous, nicely well-behaved functions, and Macau's are like square root of t, and Sasha and Dylan have a tight proof for that for the IID case. Okay, so our recipe then for good decision making is forecast things you care about, but then add this calibration variable. That will mean that you can put in regression variables and trust that the normal equations will hold. And the regression variables describe how you could be making a bad decision. So I think it's the same recipe that you gave yesterday. Then that will be a way that you want to, you will solve that. You will have protection against those bad decisions. That's part of your bets. Okay. Okay. So the summary then is, if you just do regular least squares with this crazy calibration variable, then your normal equations hold, or Macau will hold. So this part is tight. This part is sort of, a stylized fact, as they call it in economics, meaning, it's sort of not really a theorem you can prove, but it's sort of a heuristic that you can follow. Okay, so that's sort of my first sort of way of thinking about, a multi-calibration and online approach. What I want to turn to next is the same thing spun differently. So the same idea, but with just a slightly different spin on it. So this is, Calibrating. So we have lots of systems that we can use for making good forecasts. In fact, when I joined Amazon, we were using a whole bunch of these to predict demand. It turned out that our forecasts weren't calibrated, but they were kind of pretty smart. So I could make it calibrated to improve it, but I couldn't figure out a better regression to make it work better. Now, it turned out a neural net could figure out a better regression, and we've been doing neural nets ever since, even though I primarily went to Amazon to escape neural nets. So wasn't very good on that escape aspect. So these don't guarantee to be calibrated to start with, but they are good forecasts. So we wouldn't want to just replace them by a grand mean, because that'd be really a disaster. That'd be worse. What we'd like to do is keep that flavor of quality that they have and make them calibrated. Okay, so that's our goal. That's what we're calling calibrating. So say that we can calibrate one of these guys if we are better than they are in accuracy, and kind of, we're calibrated in some sense. Now, it's not actually quite that definition, but keep that in, I could be a little more precise. Okay. Okay. Yeah. So recall our initial 0-1 sequence and our better forecast, 0.1, 0.9, 0.1, 0.9. We need a way to describe the fact that this better forecast is, a win. And the natural thing is, I'm doing least squares, so I'm going to talk about quadratic error. So we could talk about it has a lower mean squared error than the 0.5 constant forecast does. But it has this sort of annoyance property that it's not calibrated. Or we could measure how not calibrated it is and say that's something that shouldn't exist. You know, it's miscalibrated by 0.1 squared. You know, if we're doing squared calibration. We don't want that to be there. So let's have our target be our least squares, you know, overall just quadratic error minus this quadratic calibration term. And after you subtract that off, that's called refinement. So I will define it again in a second with math. But the point is that the refinement is how good a forecast is if it, after the fact, was calibrated. So to make that precise, we can, you know, go back to classical statistics where we talk about expectations and biases and stuff like that. And the bias is how far away an expectation is from what we claim it to be. And if we look at the mean squared error, the key point is that is our bias squared plus a variance term. So classic statistics, you know, it just says that if you look at the L2 norm, it's your mean squared plus your variance. Okay, so here, when we go to binary sequences, our mean squared error, you know, probably, you know, showing how easy it was to be published back in the dark ages. You know, somebody came up with and said, hey, how about we measure binary sequences by mean squared error? His name was Breyer. So since then, everybody has called it the Breyer score. You know, the most trivial publication we possibly have. So our variance will be called the Breyer score. We've already seen the bias. That's the calibration that we're all very familiar with. And probably the new thing is refinement. So refinement is going to be this variance term. Okay, so you know, just write it out in precise symbols. Our Breyer score then is how far away our forecast is from the outcome, quadratic error. And you write this with projection operators, it works really elegantly. And the calibration is how far away our forecast is from the empirical frequency. And the refinement is how far away our outcome is from our calibrated version of our forecast. So the way to think about this is I make a whole bunch of forecasts. At the end of the day, I say, well, you know, I said 0.7 a lot. I really wish I'd said 0.72. So let me go through and rewrite history. And that would be my rho function. Now I'm going to have a lower least squares. So I do that for every possible constant. And now I have a way to convert my forecast. My rho function converts my forecast to what I would have liked to have said. And this then is kind of, you can't get rid of. That's oftentimes going to be, you know, just intrinsic noise in the world that, you know, unless someone can tell you some magic new pattern, you're never going to get rid of it. But the calibration kind of, we're arguing calibration of 0 is a reasonable target. That's plausible. So we'd like to have a forecast that doesn't have errors in the calibration site. Okay, so calibration is fixable after the fact. Can we fix it as we are going along? Obviously, the answer is yes, because we've been talking about things like this for a while. If we just give some names, you know, K for calibration, R for refinement, we'll say a new forecast calibrates some old forecast if its quadratic error, its Breyer score, is better than the refinement. So what that means, it's got to find the same patterns that Y hat finds, and it's got to have, say, 0 calibration error. Or if it wants to, it could find a cooler pattern and have some calibration error, but you know, that would be sort of a stupid way to solve it, but it's possible. Now, obviously, I need little o of, you know, terms and things like that, because I don't necessarily want to beat it exactly, but you know, with a little bit of swap would be nice. Yeah.
So I had in the online thing, somehow.
This is everything's online. Yeah. So I need to be able to figure out why tilde is online also. So I will be told y hat.
So we don't know what R of y hat is.
We don't know this answer until after the end of the day. And we, in particular, most important, the key thing that goes into that is this, calibration, this bias corrector. We don't know that. That will keep changing as we go along. Okay. So y tilde then has found the same patterns that y hat built into the problem without being miscalibrated. That's sort of the idea of what it's doing. It doesn't have to be calibrating. It just has to make sure its quadratic error is better than the refinement. So it's
So just sanity check. If y hat itself is perfectly calibrated, then R is equal to the prior square.
And so we could just return y tilde or home free. So
Right. But you could even hope to beat.
presumably you could still beat it. Yes. Yeah. So it would just be a battle of accuracy. So a calibrated forecast, Cala beats itself. And that, okay. Obviously, we can talk about now Cala beating more than one for, it's going to be very close to multi-Cala beating, and multi-calibration. Same story for each one of them individually. We want to say that our quadratic error is better than any of their refinements. Okay, now here is, I think this is so far the only second embarrassing, complexity thing that I'll be doing. So how can we achieve a Cala beating forecast? Well, what I do is I take all my competitors, I chop them up into little bins. This one said approximately 0.7. This one said approximately 0.2. Put those into one bin. Now, I've taken my time series, chopped them into bins. On each of those bins, compute the average. That algorithm will Cala beat each and every one of the forecasts that go into it. That algorithm is exponential in epsilon. So it would look like 1 over epsilon raised to the number of experts that we're trying to beat. This is not really an effective algorithm in terms of complexity theory, but this is truly the entire algorithm, and the proof is about that long also. Sergio really likes this, and he's convinced me that I should talk about it anyway. So I would prefer doing it with regression. You have to then be a little more careful and things like that. So you can get the same answer using regression at a complexity that would not be an embarrassment.
Sorry, so clarification, so these aren't just like level sets, non-intersection buckets, you're looking at like all possible.
So all possible intersections.
All possible intersections of buckets that are with epsilon.
Oh, yeah.
Okay, yeah.
Yeah, so it's sort of, if it was two-dimensional, it would just be a bunch of little squares.
Okay, and why, like, what happens if you just look at non-intersection? Like if you look at level sets of with
Because
epsilon?
the problem is that then I will be sort of in two buckets at the same time. I'll be in a bucket that's sort of a row here and a bucket which is a column. And I don't know which tune I want to dance to. The average of the row may be 0.7 and the average of the column may be 0.2. And if I only worry about the row, I announce 0.7. Only worry about the column, I announce 0.2. But I got to announce both of those at the same time. If we've been a algorithm, have the talk to do that. And then actually what you described makes sense. And you basically are saying, here are the bets that I worry about. And you could then solve it with that way. So, but I'm going to be going into more complexity disasters soon. So that's why I wanted to not really worry about this one minor complexity disaster. Okay. So, Cala beating things is easy. There are actually even effective algorithms for it. The problem, though, is that if you use this algorithm just described, it's going to generate something that will calibrate all the forecasts that went into it, but it's not necessarily calibrated. So something could calibrate it. Well, then something could maybe calibrate the calibrating of that. This keeps going on, and we worked for a long time trying to say it converged really fast. And eventually we gave up because we were accumulating epsilons faster than we could get rid of them. So what we want to do instead so when I start this infinite regress, is we want to do a fixed point like we did before. So if suppose I had C, which calibrates just A and B, well, if B happened to be equal to C, then I have something which calibrates itself. That means that its Breyer score is better than or equal to its refinement. The only way that can happen with the same forecast on both sides is have a calibration of 0. So if I have C in as one of its the things it's trying to beat, we cut the infinite regress off, and now what I can do is I can calibrate a collection of forecasts and be calibrated, which means I'm protected from somebody else coming along and calibrating me. Now, they could do it by actually being smarter and having better patterns. I can't stop that. But at least they can't say, every time you said 0.7, if you said 0.8, that would be better still. Okay. So for any set of forecasts, then, actually, this is basically the proof in the previous one. We can beat that set and be calibrated. Now, the problem is that this one is a fixed point. We can't do it just linear operator like I did before, where I could say, ignore the fixed point, just pretend it's algebra. This one is an honest fixed point. So, everything like this, what the fixed point is trying to do, we have, say, 2 inputs. C, we'd like to have that be the output of this. I don't know what the A is doing there. I guess, let's pretend there's no A there. And the natural thing to do is just do a fixed point. That unfortunately gets us into the complexity space of p-pad and fixed point problems. So we're going to actually do a slight modification and do something that is sort of like a fixed point, but using linear program. So what we want is we want to say that we'd like to have x minus g. That's our quadratic error that we'd like to see. I want to say, can I find some distribution which will actually have a smaller quadratic error, no matter what the outcome is? This was like the martingale thing that I mentioned earlier, where I don't need to know what the y is to be able to say that I can always beat this thing here. Now, this can be solved by a linear program. We call this an outgoing distribution. And what it boils down to is that we have sort of space of forecasts. If there's a forecast in the middle, then the outgoing distribution is something that on average equals that point. But if it's on the edge of the thing, then it's something where it pushes things towards the outward direction. Okay, so this, you can show existence of a outward distribution using minimax.
Sorry, really high level question. I got a little confused. Are you calibrating online, or is it like you do? Yeah, so at each step you do the bin updates where you're looking at all the inner.
Yeah.
Thank you.
Okay. Now, if we do the traditional approach and just do a Brouwer fixed point, we'll end up with a deterministic forecast. So our forecast, I've all probably talked about so far, but it's random. It could be kind of drastic random. It'll say sometimes 0.2 half the time and 0.7 on an outcome of a coin toss. It's not just sort of randomizing some insignificant bit. It's randomizing on a sort of full distribution on the entire space. Okay, so we could get rid of that randomization by doing a proper fixed point. That unfortunately means that we are into the sort of p-pad world. And that will generate a weakly calibrated that Sham and I did a while back. And now what you could do if you want to kind of do both is you get this weakly calibrated point, you randomly round it to some discrete points, and now you can get something that is traditionally calibrated and weakly calibrated. And this is probably more definition of calibration you ever really cared to know about. So let me, I think, just sort of summarize it. That if we just do this simple binning trick, we end up with something that is not calibrated. If we do the distributional thing using linear programming as our tool, we end up with something that is calibrated, but it has the problem that it's seriously randomizing over a wide space of possibilities. And this bugs statisticians. You should never be making a forecast of 0.2 half the time and 0.7 half the time, when if you average those, it would have a lower quadratic error. So we know how to beat this. Take the average of all its randomizations, it'll have a lower quadratic error. But then it could be, Calibrating, et cetera. So we can remove that by doing the Brouwer fixed point. But that's a computationally complexity harder problem. And if we randomly round, then we get something that's both classic and regular. Okay, so that's Calibrating, which if you want to do it seriously, you use least squares. I was doing the exponential algorithm instead. Okay, cool. So let me turn in my last 6 minutes to my third topic, which is about what should we be calibrating? So what is the thing that we want to make good forecasts of? So I'm on Amazon, so obviously the key thing that we want to be fair about is, say, hiring. Hiring is seriously economically important. We'd like to have that be fair. Luckily I'm not in HR, so I don't truly have to worry about this. But I can, as a theorist, talk about it. But I'm going to pretend that we're talking about college admissions because the language is a little bit easier to talk about. So what we should calibrate. So I'm going to suppose that we're thinking about our inputs to our decision making, namely the SATs, and then we have what we'd like to accomplish. Our output, the Y variable we really care about is, traditionally freshman first year grades, so the GPA. So it's easier to talk about SATs and GPAs than it is to talk about hiring algorithms and then success at the first performance review. We all understand GPAs in language well. Okay, so the idea is we'd like to use a prediction or SATs. The Y variable we care about that we'd like to be sort of traditionally calibrated over, that we'd like to be fairness we're about, would be our grades. But I'm a game theorist oftentimes, and so one thing we care about in game theory is incentives, and we want to make sure that we are treating people fairly as far as an incentive is concerned, meaning that we want to say that I'll be using, I think, blue and orange for my two groups, following your lead. So we want to have the two groups, blue and orange, have the same motivation to work hard to get into college. We shouldn't have it set up so that one of them has to work a lot harder than the other one in order to get past the fence. So we'd like to have that sort of incentive fairness rather than just simply outcome fairness of saying that the prediction of GPA based on SAT is fair. Okay, so the easiest definition of fairness or lack of fairness would be if the forecast for GPA, when we know that the SAT is X for either group, isn't equal. So this violation of fairness is one that Richard Posner argued you don't have to worry about violations of this sort because, yeah, rationality. No one would ever do this. It just wouldn't happen. Why look? It just doesn't occur in the world. This is a over the top belief in the efficient market hypothesis. And I was at Chicago for long enough to actually see this used as legitimate arguments in conversation where it's like, yeah, we don't need to look because we know it will never occur. It's a violation of the market. And if we don't ever look for violation of the market, well, we never have to worry about finding them.
Maybe misunderstand something, but shouldn't it just be true? Yeah.
Well, no, it should. So if your SATs are, so if you're thinking about decision making, so then let's go back to Amazon hiring, that if there was a group that if we hired them would perform better, we want to hire them. So the most extreme form of this is I was in Vienna and Academy St. Martin's in the Field had a woman conductor, and that's a pickup group. She'd picked up almost an entirely female orchestra, and it impressed Vienna like crazy. They were, they made her stay for 3 overtures, encores. And that was because she was picking people that were based purely on talent. This was back in the dark ages when Vienna actually would not hire women. So the argument is that, efficient market makes it go away. Clearly wrong. Yeah.
Answer here. So why, I mean, it could be that really the true expectation here is not just the predicted expectation. The true expectation is different when you condition.
Well,
So I'm
remember,
not sure
the SAT is an arbitrary definition. So SAT is meant to be a forecast of GPA. So you have to take that as read. The thing is SAT is a forecasting problem.
I think the question is maybe like, what if one group had access to, a bunch of SAT training courses, and the other one didn't, and so their SAT score is a bad predictor, and so you would expect that they-
Then hopefully the hope is that the SAT knows how to correct that. That's what I mean. I'm going to argue something different. So these are all good points. So let me get to my end. I argue.
Does he take this is what I'm studying. I maybe just completely misunderstanding the SAT, but does SAT take the group membership as an input?
So I thought
So to some extent, in order to achieve this, probably the SATs would want to actually, it would be much easier to achieve the equality if they actually had the group membership.
Okay.
So that make their life easier. Okay. So, this Posner argument annoyed Ricky and me. And so we kind of did some work to try to show that this doesn't work out. And that's what I'm, talking about. And in particular, the key point is that if you have equality, so if you have achieved equality, so you are, say, hiring people equally likely based on the outcome of the test and they're performing equally well, based on the outcome of how you admit them or whatever you do, you still have the problem that it hasn't been fair as far as skill is concerned. So if you achieve this goal, the thing that you kind of, in your heart of hearts, probably think that goal is achieving isn't. Namely, if you have two people with the same skill level, whatever that means, but same intrinsic ability, but they're different types, you could still have discrimination as far as that's concerned. You could still say, I'd prefer being in this group over here. So achieving this goal does not guarantee that goal. The only time that you actually achieve both at once is if you have a perfect forecast. If your forecast has any noise in it, then you can't get equality in both of these. So, what I'm arguing is we'd like to, have SAT be calibrated given skill. Now, what we're seeing here is that, regular regression minimizes F, to predict Y. Reverse regression minimizes G to predict X. And even if F and G are fit by linear functions, F is not the inverse of G. So the thing which minimizes one of these is not the thing that minimizes the other one inverse. And that regression to the mean effect is now saying that this is now where I'm arguing this really is a regulation issue because Amazon wants to make good forecasts for good hiring decisions. Society wants to have good incentives and fairness for skill definition. So we're all being treated equal. And we can't achieve both of these. So sort of regulation has to my mind, push that we are forced to use this one in spite of the fact that colleges and employers and everybody else would prefer using that one. So this problem is regression to the mean. And let's see, I think, so I just kind of end with here, that then you don't get skill. So probably the best way to do that then is simply do the regression the wrong way around. What you want is you want your SATs to be calibrated given the outcome variable, so given their GPA. So this is a different form of calibration than the more traditional one that universities typically worry about, which is they would like to know that everybody they admit is likely to succeed. That's their forecasting problem. This is arguing for incentives and game theoretically trying to keep everybody fair. We want to go the other way around. Okay, so bunch of papers. I like on screen, click on these things, like how? I actually saw someone printing out with blue underlines that on paper that you really truly can't print on. So, if you go to my website, I think there's under Simon's as a talk, and probably we can post somehow. And the key point is there's one Foster, me, there's another Foster, Dylan, and there's a third Foster who did also least squares. Okay, so takeaways, crazy calibration is neat. There's multiple ways to calibrate, and do your regressions the other way around. Okay, thank you.
Great, let's take.
There's going to be some serious and long
There's going to be time left. Let's go to the 11 spot, and she'd be happy to read that. Well,
Exactly. Discussing why. Reverse calibration. Could you just go to the reverse?
Other people to recognize this.
We're also
So
yes, we have a whole discussion.
Okay, cool.
We can look at like scenarios and